Hi, in this video, I'll present the idea that an indefinite integral question is in fact a differential equation question. And from there, show the importance of the existence and uniqueness theorems. Let's take an indefinite integral question like this one. Compute the integral of x squared dx. That's the same thing as asking, find a function y such that y prime is equal to x squared. That's a differential equation. The highest derivative of y is y prime, so this equation is first order. Also, y prime and any y, they appear in just linear form, so this is a linear equation. The fact that we have an x squared does not make it nonlinear, because for purposes of classifying a differential equation, we only look at y and its derivatives. This is a first order linear differential equation. And the answer is y equals x cubed over 3 plus c. If we graph a whole bunch of these x cubed over 3 plus c, we get several curves like these. All of these are solutions to the differential equation, in the sense that at each point on the curve, the slope y prime satisfies the condition y prime equals x squared. That's nice that we have a whole bunch of solutions, but having a whole bunch of solutions can also be a problem in the sense that if we're gonna do something about the function, for example, if this equation comes from some sort of practical question in science or engineering or finance, we don't know which function to work with in the next step. With just the equation, we're missing important information as to how to choose which function it is. Of all these curves, we need one more piece of information that tells us which one to use. And that usually comes in the form of an initial condition. For example, we could also be given the additional information that y at x equals 0 is equal to 1. That is called an initial condition or initial value. And this whole thing is called an initial value problem. Given the additional information that says the curve has to pass through the point 0, 1, x equals 0, y equals 1, we know that this curve right here has to be the solution. And that curve is the x cubed over 3 plus 1 curve. That means all the other curves are not the solution. There's only one solution, which is this curve that passes through the point 0, 1. The other curves don't pass through 0, 1. So I have my function, I put it down on my paper. And if anyone asks, what is the value of the function when x is equal to 2? Then I can just plug it in. I get y is equal to 8/3 plus 1, which is something like 3.667 right here. Great, that makes sense. But are you sure? What if, bear with me here, what if there's another curve that's similarly shaped with the slope that satisfies this condition, but it just sort of like slightly off of this curve. It cuts at the same point 0, 1, but along the way, it sort of bends off and it goes off over here or something. How do we know that curve does not exist? And then if we have to predict what the value of that curve is when x equal to 2, the answer would be like that point over here. Instead, how do we know that alternative curve does not exist? That's why in differential equations, we pay a lot of attention to the existence and uniqueness theorems. The existence part means we need to identify the conditions under which a solution exists to initial value problem. That way we know whether it's worth spending time searching for a solution. For this particular example, we don't have to worry about existence because we found it. is x cubed over 3 plus 1. That satisfies the differential equation, and it also satisfies the initial condition of y of 0 equals 1. But we still need to make sure it's unique. We still need to make sure that this possibly second solution does not exist. That's why as you go through this differential equation course, always take note of the existence and uniqueness theorems. Now for this particular example, luckily, the conditions for existence and uniqueness are both met. We don't have to worry about that extra curve. It doesn't exist. So let me close out this example by applying existence and uniqueness to this particular situation where we have a first order differential equation. For a first order differential equation, we have some sort of y prime, some sort of y, and some sort of x mixed somehow. Well, do some algebra on them and isolate the y prime. You isolate the y prime, then all the x and y are on the other side. So basically you end up with y prime as some function of xy. And then you have your initial condition that y at some x naught is equal to y naught. This is your initial value problem. There's the initial point. The existence theorem for this kind of initial value problem goes like this. If your function f of xy is continuous for the area of x naught plus or minus some delta, so plus some delta this way and minus some delta that way. So we're looking at x naught minus delta and x naught plus delta for x in between those, and also for y in between some minus epsilon plus epsilon from that. So y naught minus epsilon less than y naught plus epsilon. All the x's are going to be between these two boundaries, and all the y's in between those two boundaries. That makes a rectangle around the initial value point. If f is continuous in that region, then a solution exists. Let me call this problem star. Then y equals fx exists. That is a solution to the star problem, the initial value problem star, in some interval around x naught. Y is a function of x, and I'm saying that it will exist a solution somewhere near here. I can't really guarantee a lot about the existence of y when you go too far from x naught. The way people write it is x naught minus some delta 1. It may be different from this delta. It's probably smaller. So the interval where the capital F is continuous is somewhere around x naught. And the delta 1 could be smaller than that interval. It could be narrower. So that's the existence part of the theorem. Now comes the uniqueness. The uniqueness says if f, and not just f is continuous, but also the derivative of f is continuous. Oh, derivative of f with respect to which one? I mean, f has two variables. It has an x and a y variable. We're looking at the derivative with respect to y. It's a partial derivative with respect to y in some region x naught, y naught. Then the solution, first of all, it exists, right? Because f is continuous. By the existence part, by existence theorem, will be unique. But again, we don't guarantee that it's unique everywhere. We only guarantee that it's unique somewhere near x naught in some interval around x naught. So we're looking at x naught minus some delta 2 to x naught plus some delta 2. We can only guarantee uniqueness for our x that's in between those two. This kind of verbiage is going to be very common for a lot of theorems in differential equations and analysis and those things. So you probably want to get used to understanding what it means. Other than that verbiage, the bottom line is existence requires f is continuous, and uniqueness requires that f and partial f partial y also continuous. So that's the bottom line. All the rest of the verbiage is just to tell you that we can only guarantee existence and uniqueness in a certain area near x naught, near the initial condition. We can't really say much about what's going on far away from it. So for our example, the equation was y prime is equal to x squared, and the initial condition was y of 0 equals 1. So that means we're looking at x naught, y naught is the point 0, 1. Y prime is already isolated. So we're looking at fxy is actually just a function of x. F is continuous everywhere. So we have existence. Partial f with respect to y is equal to 0 as a function, is equal to the 0 function. So it's also continuous everywhere. And so you have uniqueness. And in this particular situation, the delta 1 and delta 2 can be arbitrarily large. I hope this helps you appreciate how important the existence and uniqueness theorems are. Any question, put it in the comments. Subscribe for more contents. Thanks for watching, and bye.